In this tutorial, we're going to look at the output of the model and do some post-processing. So we're running the North Pacific simulation. So I'm going to go in CD-ROMs example in Pacific. And at this point, there we have our output, which I have moved to a directory called outspin. And as I moved the output, I also removed the history files and kept only the average files because those are the ones that I care about right now. I'm going to use this initial run as a spin-up of the model of the North Pacific. In this particular case, I extended this run to cover over 6 years of integration, so it's beyond 10 years. And I want to start working with this model output. To do that, I'm going to go in the MATLAB directory, and I'm going to open a new file that I'm going to call npacific underscore let's call it spinup.m. And this is going to be a MATLAB script that I already started editing actually, which is going to help me to work with the current output. So the first thing that I do is I load my grid as usual. I define the output directory where the run is stored, in this case the following. I then produce a list of all the files that are contained in the output directory by using the command rnt get file names. This command wants two input arguments, the output directory, and then a string that characterizes all the files that are part of the output. So actually let me execute this in a MATLAB window. So I'm going to go again in the ROMs examples npacific -matlib and run MATLAB. And I'm going to paste this command. So now I have a list of these files, and there are a lot of them, 66 in this case. Now the next thing is I'm going to do is of all these files, I'm going to throw away the first 31 years also, because as I compute the spin-up climatology, for example, I don't want to keep the first 30 years just because I can do it. In general, of course, if you had only 10 years, you would probably throw away the first 3 years, which are really a spin-up, and then use the remaining to kind of compute a spin-up climatology. So I'm going to throw up the first 31 years to be safe, and then I'm going to produce a control array that has with this output. So I'm going to do that, and if I look at CTL year, I have about 65 years. At this point, the next thing that I want to do is I could load, for example, any variables. Okay, so for example, if I load the zeta, do rnt load var CTL, comma, and then I can do 1 to length len gth of CTL dot time, and I'm going to load the variable zeta. Okay, I screwed up spelling here, CTL. So I'm loading the free surface, for example, for the whole period. And it didn't take too long. And now I can make a figure, for example, of the mean sea surface height. I'm going to take the mean in the time domain, GRD, and I'm going to put a c-axis here from minus 0.6 to 0.6, for example. And here I get a nice climatological sea surface. You can see the North Pacific current here, the California current, the Alaskan gyre, the Kuroshio washer extension region. So it more or less looks very good. If you did only a 10-year spin-up, you probably would notice some difference from this longer climatology, and that's because typically spin-up in the North Pacific will take more than 10 years. And so that's to be expected. But for the purpose of your tutorial, running 10 years is probably sufficient to understand the main points. Now, in this particular case, I load the entire zeta, and I can compute, for example, the seasonal cycle by going here. Well, let's copy this string here. Let's go and edit. And I can compute this, and then I can compute the seasonal cycle, zeta anomaly and zeta m, by using this function, remove seasonal cycle of zeta, comma, CTL dot month, comma, and then 3, which is the place of the time index. And this, what it does, it removes the seasonal cycle and it produces an anomaly for zeta, which I'm going to call zeta. And then it also produces a 12-month climatology, which is stored in zeta m. So then I can look at both. So if I do that, go in MATLAB, press that. And number 3 means that the time index of this variable is the third index. As you can see, it has the two spatial dimension, and then it has the time. Okay, and so now I can look at the January climatology, for example, by just instead of doing mean of zeta, I can look at zeta m of space January, and this is what it looks like. Okay, so this is of course I could do climatology for all the variables, but instead of doing it by hand, what I'm going to do is I'm going to use a particular script to generate climatologies of all things that I care about. And so let me go here. And the way that I'm going to do this, I'm going to use a function that it's called rntp make klima. So the first thing is I'm going to decide that I'm going to put some code here. I'm going to create a directory that where to store this climatology of the model. And in particular, I'm going to put it inside the outspin directory. I'm going to call klima-spin. Okay, and then I'm going to assign a prefix for the output files that will contain the climatologies, and this prefix will be something like npacific klima. Then I'm going to make a list of all the variables that I want to compute a climatology for, and in this particular case here I have salinity, temperature, UV, U bar, V bar, all the model state. In addition to that, I'm also compute climatology for the sea surface heat flux, the heat flux that the model saw, and the sea surface salinity flux. And these are important because I'm going to use these later to recompute a corrected climatology of the surface flux. Because if you remember, this particular integration uses a salinity correction and a temperature correction at the surface to ensure that the fluxes at the surface are such that the climatology of surface temperature and salinity matches the one of the observations, or reference climatology, in this case the World Ocean Atlas. So that means that this particular flux here, if I make a climatology out of this is going to be the net heat flux that is necessary, for example, to maintain a seasonal cycle in the surface temperature that doesn't drift in the model, and it's consistent with the depth of the mixed layer of the model. Okay, and we've seen this a little bit in class. We've talked about this. So once I have these parameters defined, then I'm going to use this function called rntp make klima, and it takes a little bit of arguments here: the GRD, the grid, the CTL, which is the output of the model, the vars, which are the variables for which you want to compute the climatology, and then prefix with the name that it's going to assign to these files. After doing that, then the last thing I'm going to do is I'm going to change directory again in my current dir. Okay, so this is just a little piece of code. So here I take the current directory. I decide where the output directory is. Then I create the output directory. I go in the output directory. I run my post processing, and then I come back to the directory of origin. So I'm going to execute this stuff now very quickly. I'm actually going to execute this first part. I just want to go slowly. F12. Okay. So now I'm in this directory here in the klima spin, and I'm going to now put this stuff here and then start the model, the post processing. And so as you can see, it's doing the post processing, and it's going to take some time to do the post processing. It takes, so you let this run for a while, and when this is run, what you will have, I'm going to stop this, and I already computed this because it's going to take some time, so I don't want to wait too much time. But once you're done computing, you're going to have 12 files. Each file is basically the climatology for the month, say, of January, February, and so forth. So at this point, what you can do is you can go back to your current directory, which is current dir, okay, And you can make a list of the climatological files, for example, by just typing the RNT get file names, the output directory of the thing, and the prefix. And now you should have files here. Let's write them. And you see you have all the files here. Okay. And once you've done that, then you can actually load the climatology, for example, F12 of the model. And so now you have the climatology of the model. Okay. So I'm actually going to put these statements in my sample script here. So I'm going to add these in here. So once I'm done with the climatology, I'm going to make a list of the files, and then I'm going to produce a CTLC of the model climatology, which is kind of handy to have. At this point, I can compare this with the climatology that I used from the World Ocean Atlas, or that I didn't use, but I computed it. And I'm going to load that in a CTLC WOA, and so that I can compare them together. So for example, I'm going to now load also this control array. So now I have CTLC and CTLC WOA. I must have made a mistake when I was loading that. Input npacific clima. Oh, it's called clim. Okay, so I made a mistake in the spelling of this file. So let me correct that. Here we go. So I'm going to re-execute this statement here in MATLAB. Okay, and now I have this. And so now I can easily compare these climatology months per month or intervariables. For example, I can load the temperature, RNT load var, and then I can do CTLC. This is the model climatology. Say I compute the whole 12 months. And I want to load the variable temp. Okay, so I compute that. I load that from the thing, and then I can take the mean temp of this climatology of the model. So this, because all the months. And in this case, I have to take the mean on the fourth index because this has two dimensions, horizontal, a vertical dimension, and then time. So I do this. So now I have the annual mean temperature of the model, and I can also do the same for the world ocean climatology. Oops, mistake. I should have defined this in a different variable. So let's do that, and then let's say the temp equals mean of temp W. Okay, so this is the mean of the World Ocean Atlas climatology, and now I have to reload the one from the model and recompute the mean of the model. So now I can compare these two, and for example, I can plot a section RNT sect Y, for example, of the model climatology of temperature, and let's say I plot a section along index I equals 60. Okay, we're going to have a tutorial on plotting in a later one. So for now, I'm just going to put some functions here. So this is a section now in the model. And in fact, I can let me change color map, pmap 5, just because I like it more. Okay, it's a little bit more clear. And let's compare that with Levitus. So let me just put this map on the top panel, and let's replot the vertical section here. Okay, so that's my model vertical section climatology, and then in the bottom panel, I'm going to plot the one from Levitus. And you can see that broadly speaking, they're very similar, although there are some differences. And if you really want to look at the differences, since now these two climatologies are exactly on the same grid, really all you need to do then is clear this and just plot RNT temp minus temp W. And by doing this, you could start seeing what the main differences are between these two variables, and you can see that in principle, you know, the 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 actual model is actually cooler in this region, okay, and warmer up here, signifying, for example, that in this particular region there is a shallowing of the thermocline in the model with respect to climatology, and here you find there's a warming in the model, meaning that maybe the thermocline is a little bit deeper, and so you have warmer water, you know, with respect to things. So this is a good way now to start, you know, checking for you know, quality and realism of your model simulation. We can do a similar analysis, of course, for salinity, and let's say salt equals, let's say we load, um, actually before we do that, let me just copy these things in my little uh, script here, F12, so this is, and then here we want to take this is the World Ocean Atlas ints, and we're going to do a mean in this case, ins comma 3, okay, and we're going to also do the temperature of the model. Let's call it the model temperature, and in this case it's not from the World Ocean Atlas anymore. And so these are the two means, and we can play around with that, and of course we can do similar things for any of the other variables. Let's try salinity, for example. Salt and salt, and we can load the salinity. And of course you can do this month by month. This is you know, not necessarily you have to look at the annual climatology, but at the annual average. But so let's try the salinity here. So I'm loading salt, and then I'm going to plot a section, for example, of the salinity in the model. And there was some issue here. Oh, and the issue is that I made a mistake in here again, because I forgot that the time index is actually number 4, not number 3. So I have to correct that. So this is just to give you an idea that I make mistakes very easily, and therefore you should never trust what I give you 100%. And let's plot now the salinity. This should work. And this is the salinity. Let's use a color map that that is a little bit easier to see. And now again I can compare the difference between the model and the climatology, like that. And Control C. First I need to clear this. And what you see again is that in this region you have that the model is actually fresher, okay, than it is up here. And this could also signify, for example, let's check what the climatology looks like. But let's look at the climatology of the model. So this means, in general, if you have a freshening here, okay, meaning that the model is less salty, that means again that this tongue of fresh water in the model is probably, you know, further close to the surface. Okay, and again that would mean, similar to the temperature, that the thermocline of the model is a bit shallower. Okay, and you see the reverse happening in the higher latitudes, like we said, in temperature. So there are some biases in the structure that depend from the fact that, you know, the mixed layers, for example, may be a little bit different in depth. Now, of course, this is the climatology of the World Ocean Atlas. If we go in Figure 3 and Figure 3, and we plot the climatology of salinity of the model, okay, we find that although there are differences, there is definitely some similarities in the structure of these fields. Although you can see, for example, this kind of subduction of fresh waters inside, you know, in the subtropics that you see in this particular, you know, figure here, is less clear in the model. Although you could see here, you could still see that there's some kind of subduction. Although it's unclear at this point if this tongue of fresher water is actually coming from the open boundary, or if it's really being subducted, from the higher latitudes. But anyway, but this is just to give you in a sense an idea of how you can start looking at the output. And so typically a good thing to do is then to create, a script where you load the data, you do some post-processing, and so forth. Okay, and it's nice to have a climatology computer from the model, because then at any particular time you can compute an anomaly with respect to the seasonal mean, and so you don't have to always reload the entire variables. Now in this case of the free surface, we did load the entire variable. Okay, but this is a two-dimensional variable. If you were to do this with the temperature, you will probably run out of memory. So that's why you want to pre-process it, in this fashion over here. Okay, so I'm going to save this script here. It's called npacific spinup, and this will conclude this tutorial on the examining the model output and doing some post-processing. Okay.